I will just ask why you label Bohmian mechanics as a fundamental theory when, as far as I'm aware, it, and my awareness doesn't stretch that far, it's not a theory of quantum gravity, at least at this point.
It's not a fundamental theory in that sense. What a more accurate statement would have been let's say, in some sense, a potentially fundamental theory. You want to understand the theory, pretend that it's fundamental and see what the world will be like if this were the theory. Stop worrying about where the theory comes from or what the deeper theory from which this theory might emerge is. You want to understand this theory, treat it as if it's fundamental.
But what features of pilot wave theory make it promising to you as the potential fundamental theory?
No. It's not it's. Let's say the world is quantum mechanical, which I think, I'm not sure how many people actually believe that ultimately the world will be found regarded as quantum mechanical, but I think I'm naive enough to say, okay, maybe it is so. Maybe the world is. I have a feeling in 1,000 years we're going to say that all of this quantum stuff was nonsense. But right now I'm naive, and I think it should be quantum mechanical. All the evidence suggests quantum mechanics is the way to go. Some version of quantum mechanics. So what does that mean to have a theory to be a version of quantum mechanics? I certainly don't want any Copenhagen-ish theory. I want something coherent, where I know what the theory is really about, and it's definitely not fundamentally about measurement and observation. If somebody gives me a theory and the axioms involve measurement and observation, and they tell me it's about measurement and observation, I can stop listening. I know it's not a serious theory. Now, so I've got the wave function, and it involves according to something like Schrodinger's equation and Schrodinger's type equation. Fine. And there has to be more than the wave function, unless you go to the many worlds route, which I think is a big mistake. So it's not hard to say there's more than the wave function, because if you have more than the wave function is given something to do. It's not everything. It's simply giving. It's sort of an object of the kind we standardly introduce into theories to play a role in the behavior of something we already have, like the electromagnetic field. It plays a role in the behavior of charged particles. Wave function definitely plays a role. It's orthodox quantum theory, the role the wave function plays. It's not many worlds orthodox quantum theory. The role the wave function plays in orthodox quantum theory is on the level of measurement. That's entirely the wrong level to assign a role to the wave function. And when you try to do it that way, you make a really complicated mess with a whole slew of axioms, measurement axioms. If you assign a role to the wave function on the level of the particles, on the microscopic level, it's very easy to do, and you just need one equation, the guiding equation. So that all makes good sense. Now suppose we come to a more fundamental theory, quantum field theory, quantum gravity, whatever. Then if it's a quantum theory, there should be a wave function playing a similar role, governing the behavior of the fundamental objects of the theory, which will not be the wave function. That's what I would consider to be a sensible fundamental quantum theory.
I'm wondering if this wasn't a crucial part of your response, Shelley, but I'm wondering if we've found a place where you two diverge, and it's your hunch that in 1,000 years people might have gotten rid of quantum mechanics, and I have a feeling that Tim won't feel that way. Am I off the mark?
I think we get into a semantic issue here.
Okay.
I mean, look, what does history tell us? History tells us some theories that were really impressively empirically successful turned out, from present perspective, to have been fundamentally wrong. Just fundamentally wrong, right? Newtonian mechanics seems to have been fundamentally wrong. Newtonian gravitational theory seems to have been fundamentally wrong. Certainly, if you believe in general relativity, you're going to say it wasn't just in detail that Newton's gravitational theory was wrong. It's in, if you think that what we call gravitational phenomena are a consequence of the curvature of space-time, then Newton was just way off base. I mean, he was completely off base, right? But nonetheless, that theory makes really good predictions. I mean, at NASA, they still use that to pilot their landers to land on Mars. They know that theoretically general relativity would make slightly better predictions, but at the level of accuracy they need, they don't care. So one thing we know is that the mere empirical success of a theory at a certain time is no guarantee that it's even, as it were, in the right ballpark at a fundamental level. Could there be huge shifts in the next 1,000 years? Of course there could. Would those shifts, I mean, part of the problem or part of the advantage that quantum theory has at the moment is that unlike Newtonian mechanics, nobody knows exactly what it is. So it would be a little easier for the word quantum theory to be inherited by the successor, right? Because you're not quite sure what quantum theory is anyway. So, I mean, there's part of this is just a semantic issue. Will they still call it quantum theory? How close will it be to what we have now? No, I don't really disagree. I don't know. Certainly, because quantum theory is the best thing we have now, the way to spend your time, unless you want to go really take a flyer and go off in some entirely new direction and cross your fingers that you'll get something empirically successful, is to think about that theory and kind of make incremental progress from it as a base insofar as you can. I think that's the best heuristic advice anybody could give you at the moment.
Yes, I suppose that even though quantum field theory has been empirically confirmed to like 14 decimal places, the 31st decimal place 1,000 years from now, they might get a major discrepancy that tosses everything on its head.
But it's not just that. Again, the theories can turn out to be conceptually wrong, but empirically right. And so I'm not talking about the failure of the empirics. You might have as it were, a theory that doesn't correct the predictions of quantum field theory, but derives them in a way and from physical postulates that are much clearer and maybe even mathematically more tractable, right? You don't get all kinds of infinities. You don't have renormalization problems. There are various conceptual problems that might go away. It wouldn't necessarily mean that the theory as it is now fails empirically, but it still might be replaced by something that just seems much more satisfactory.